Okay, welcome to my ninth video in transformers and in electrical machinery. I did the example with an all-load and a short circuit test with in a previous video, and now I'm going to show you what is voltage regulation. I'm gonna explain a little bit about theory and all that, and in my next video you're going to see the full picture of the voltage regulation. So let me just I'm gonna use the book because my English is bad and I don't want to say something wrong. I think I said some stuff that I didn't meant to say, but you know, my English is bad. I know I don't speak good English, but I like doing videos in a foreign country. So most of the load connected to the secondary of a transformer are designed to operate at essentially constant voltage. So if you want, you want to have, I don't know, 110 or 20 volts, I forgot what is the distribution, voltage in America and US. I think it's 120 or 110, but if you want to design it, you have to make a smaller internal impedance of a transformer, because if the more current is drawn from the transformer, the terminal voltage can vary up and down depending on the nature of the load. So there is something that we must do about that. I don't know if you ever measured the voltage in your power outlets, but it's not usually always the same. Sometimes it goes higher, sometimes it goes lower, but everybody says, well, that's because the resistance of the wires, so there is a voltage dropout. I mean, that is also one factor, but the biggest, I would say, problem is with the transformer that it doesn't have a constant voltage on the secondary, because sometimes the current is drawn more, and then the internal voltage dropout on the transformer is affected on the load terminal. So now if you look at this picture, so this is a basic principle of a transformer. It has an internal resistance, impedance, and here we have a primary and the secondary side. Now if we open the switch, so we disconnect all the loads in households and all of that, then the voltage on the secondary V2 NL, this is no load, is equal to V1, the primary voltage, divided by the turns ratio. So if we didn't connect the load. Now if we close the switch, then the V2 is now V2L. So it's a load voltage. We have a load voltage, and low terminal voltage V2L is going to change with the nature of the load. So there is an internal impedance, so this also plays an important role, and also depends on the leading and the lagging power factors in these electric circuits. Okay. Now this voltage, so this is the voltage dropout, is essentially because of the IZ voltage dropout in the internal impedance of the transformer. and if you, for example, connect a large if you, for example, connect more and more light bulbs in your house or in the area which this transformer is connected, then the voltage dropout could go low, and then the light bulbs will glow with diminished light. So, and to reduce the magnitude of the voltage change, the transformer should be designed for a low value of the internal impedance. So, if you want this to work on a essentially constant value, this here, the internal impedance must be as low as possible, and we have to make that in phase with V2. But I'm gonna say something about that later on. Now, a figure of merit called voltage regulation used to identify this characteristic of voltage change in a transformer with welding. The voltage regulation is defined as the change in magnitude of the secondary voltage as the load current changes from the no load to the loaded condition. This is expressed as follows. Now, there is a formula called voltage regulation, and engineers are always doing this formula. So they sometimes connect a capacitive load, they sometimes connect the more inductive load. So if you have a resistive load, that doesn't make much problems, but capacitive and inductive loads, they can change this terminal voltage V2 very much. So they put some capacitive load on the secondary, and they see how this is going to change. They put some inductive and also see how this is going to change. And it's in this formula. So this voltage regulation is usually measured in percentage. So if you want to get this in percentage, you just multiply this by 100. In my next video you will see what do I mean by this. So this is how the terminal voltage will change. Now engineers usually have a leading power factor and lagging power factor on the load. So they put, for example, a leading power. This will be negative, because for a leading power it increases the voltage or capacity, and the load will this no load will be a little bit smaller, so it rises to some it rises to the load voltage, but you'll see that in my next video. And yeah, these absolute signs are saying that it doesn't matter in which phases are they, it's the magnitude of the voltage that is very important for us. So in the best situation for us is when this is 0. So when the load and the no load are in the same value, but it usually is not the case. And for example, if you have more leading power on in the area where this transformer is used, then some engineers in your electrical distribution company can go there and can regulate this situation by giving lagging power, so you will have a better power factor in your area, and and vice versa. Okay, this is voltage regulation, but if we reduce the secondary side on the primary, that's why you have V2 prime and V2 prime low L, V2 prime L. So these are the reduced values from the secondary to the primary. And these formulas are the same. Now, usually the load value, engineers first have to make a transformer so that the load voltage will be also the rated voltage. So engineers usually design the transformers so that the rated voltage is the load voltage of the transformer. So for example, if it is not designed the same, if you have a transmission transformer, so and the distribution transformer work on the same principles, but they are designed differently because of the application of that transformer. So we usually say that the load voltage is the rated voltage which the engineers and the manufacturer designed on the nameplate. Now, this is a formula that the primary voltage V1 is equal to the V2 prime. So this is the this load voltage here, the terminal voltage, plus I2 prime times the resistive equivalent part of the internal impedance of the transformer times the plus J I2 prime times the reactive impedance part of the transformer. Okay, now if we just for the rated voltage on the nameplate put instead of the load voltage, we can measure what is the voltage regulation in percentage. So we just multiplied by 100 and then you get voltage regulation in percentages. That's nothing more to say. And what are these angles? Theta 2 plus theta equivalent 1 equals 0. What is this? Now, here you have a phasor diagram. So this is the phasor diagram, as you can see. Now, V1, this primary voltage 1, is going to be the highest if the internal impedance, the equivalent 1, is in phase with V2 prime. Now, this theta 2 is the angle of the load impedance. That's what I talked about earlier on. So this theta 2 depends on the load. It can be inductive, it can be capacitive. The best thing is this to be you know that the power factor of 1 is best when this is equal to 1. But there is I think in every AC appliances, all alternating current, it is pretty much impossible to get the equivalent phase equal to 0. So in AC you always have some capacitance inductance. Even wires have some inductance in AC, and capacitance with the ground, they always have some capacitance. So I think for me it's virtually impossible to get it that equal to 0. Now, and theta equivalent 1 is the phase of the internal impedance, and to get this V1 and so if you want this V1 to get its magnitude as high as possible, then this I2Z equivalent must be in phase with V2. So this theta now look at this formula here. As you can see, V2 plus I2 are equivalent 1. Now, for the resistive elements, there is no phase shifting. But for the inductive, and of course this is inductance, you have phase shifting about of 90 degrees. So this plus this is equal to I2 prime times Z equivalent 1. And this blue circle is here. Is the locus of V1. So this I2 Z equivalent can go something like this. So it's not a perfect encircle, and that's how the V1 is going to change dependent of the load. So the biggest magnitude V1 is going to have from here to here, and in order for this to go here, I2 prime Z equivalent go to here, this theta 2 plus theta equivalent 1 must be equal to 0, so it goes here. And so if this is equal to 0, then theta 2 is equal to minus theta equivalent 1. So if you have plus 30 degrees of the power load, phase shifting power load, then you want to have an internal resistance of minus 30 degrees, and then this V1 is going to be highest. Okay, and I think that's it. I don't know what to say anymore for this video, and I hope you enjoy it, you learn some things, and in my next video I'm going to do an example, and everything is going to be much more clearer. So see you in my next video where I'm going to do an example. Bye.